There we go. Okay, so chapter 9 is finishing up with 9.5, solving trig equations. We are going to do quite a few different types. I don't know if we'll get through these notes today or if we need to continue tomorrow. We'll see. But we are going to be having a quiz at the end of the week over 9.2, 9.3, and 9.5. So warning, that's coming. What's great about trig equations is that they follow a lot of the rules of just normal algebra until the very end, and then we're going to need to use our unit circle. So if you do have a picture of the unit circle, hopefully it's in your brain, but that might be something that would help you. What we're going to do is I'm going to show it to you a few different ways so that we can utilize our algebra as much as we can. So if you see something like this, it says find all solutions of the tangent of x cosine of x minus the cosine of x equals 0 on the interval from 0 to 2 pi. So most of these, you're going to see that notation. That just means one loop around the unit circle. What are the answers that will make this work? So that's all that says. So this is just kind of, hey, look at the unit circle. What are your answers? Now I'm going to show you a few different ways. I'm going to let x equal our tangent. Well, instead, since we already have an x there, let's call it y. And then let's let z equal our cosine. Now, wherever we see a tangent of x, I'm going to take it out, I'm going to put a y. Wherever we see cosine of x, I'm going to take it out, I'm going to put a z. And if I asked you to solve that equation for y and z, let's think about algebraically what we would do. Well, the y's and z's are touching at the moment, but one of the things we can do is factorization. If we factored out a z, we would get y minus 1. And what's great about factorization is if we have the factors equal to 0, that is a key, always try to get that equal to 0, at least most of the time, we can split it apart. So I know that z equals 0 or y minus 1 equals 0. So I get two very distinct, very simple equations, either z equals 0 or y is equal to 1. Now, I've taken out the trig. I've just made it kind of reflect an algebra problem. And now we got to put the trig back on. So what was z equal to? Well, z was equal to the cosine. So now we're going to go cosine of x equals 0. What was y equal to? Well, y was equal to tangent. So let's put that back on. Now that the trig's back in, at this point, now we answer the question finally by using our unit circle. So let's look at this. On the unit circle, where is the cosine equal to 0 when we go one flip around our circle? Well, the cosine is our x value. And so on the unit circle, that occurs at pi over 2. We're also at 3 pi over 2. So that's where the trig comes back in. Now let's think about where is the tangent equal to 1? Well, the tangent is positive in both the first and the third quadrants, and the tangent is 1 at the 45s in those locations. So that would be at pi over 4. And the third quadrant, pi over 4, is 5 pi over 4. So we have 4 different answers to our equation. If we look back at the top, if I put in pi over 2, if I did the tangent of pi over 2 times the cosine of pi over 2 minus the cosine of pi over 2, I should get 0. Same thing if you plug in any of those values into your top equation, you should get an answer of 0. Now let's go backwards and let's do the problem without using this substitution method. If you just saw this, what you can also do is you can think of each these, those are stuck together. Those are stuck together. We can take out a cosine of x from both of those pieces. We are left with the tangent of x minus 1. We're left with the cosine of x equals 0, which takes us right back to this spot. And we're left with the tangent of x minus 1 equals 0, or the tangent of x equals 1, which brings us right back to that spot. So you can use substitution to clear away the trig and allow you to just solve it without thinking about the trig till the final step. Or you can factor out the trig and solve it the same way. You should get the same exact answers. This would give you pi over 2 or 3 pi over 2. This one gives you pi over 4 or 5 pi over 4. So you get the same answers. The technique and how you do it is up to you. If you can't see how this is factorable, but this makes more sense how it's factorable, do it this way and come back to the trig at the end. So it's up to you. I'm going to do each problem both ways so that you can see how you can do it both ways, and you decide from there. I don't care what method you use. This way, there's a trig, a calculus thing called use substitution that is helpful. It's up to you. Okay, everybody okay with example 1? Anybody have any questions about how we got the answers? But our final answers are these 4 values: pi over 2, 3 pi over 2, pi over 4, and 5 pi over 4. Okay, let's do another one. Now, when there's only one trig function in the problem, that would be our substitution. Okay, so let's go ahead and I'm going to call my variable u. I'm going to take out the sine of x. I'm going to replace it with a u, and I'm going to just solve it using algebra. So I'm going to put in a u. Every place that I see a sine, take it out, I'm going to put a u in. Now, just solve it. Let's get the u's to one side, the numbers to the other side. Let's subtract a u from both sides. Divide by -2. Once you have solved it and it says your variable equals or u equals, now it's time to put the trig back in. Now remember, u is equal to the sine of x, so that's where it goes right here. And only once the trig function says the trig function equals some number do we actually use our unit circle. So you're asking on the unit circle. So where on the unit circle does that happen? Now, do you see where it says the words all solutions? The ones that we're going to concentrate on are more like example 1, where they go from 0 to 2 pi, like one loop around our unit circle. But I wanted to see you this notation as well. If it says all solutions, we're going to still find it on the unit circle, just one loop around. The sign is negative square root of 3 over 2. The sign is negative down at the bottom 2 quadrants, quadrants 3 and 4. And it's negative at the 60s that are down there. And so we get 2 values. If it didn't say all solutions and it just said that 0 to 2 pi, our answers are going to be the angle measures of 4 pi over 3 or 5 pi over 3. Okay. Now, here's where it gets all solutions. Let's go back a few chapters, I think chapter 7. We learned that coterminal angles occur every 360 degrees. So all you do to cover the all angles, you just tack on something called 2n pi, where n is an integer. And so you do it for both of them. You still do the same exact thing, but you just tack on a 2n pi. What does that 2n pi do? Well, that 2n pi covers every single iteration of 4 pi over 3. How do we get to 4 pi over 3? Well, we can do a 360 loop one way or the other, okay? We are going to focus on stopping here, but I do want you to see that's how you get all the solutions, by using that coterminal angle thinking.
What does it say at the end at 4 pi over 3 plus?
This right here, that is, n is an element of z. That means element of, and this means integers. So that's just a notational thing. N is an element of z means that n is an element of the integers. Now let's go back to the problem, and let's not use that u substitution. Let's just solve it directly. So I'm just going to write it. I just want to show you two different ways to solve these problems. So this is our answer. Let me show you a separate way to get the answer. So let's rewrite the problem, and let's do the problem directly. If I subtract a sign from both sides, I get -2 sine of x. I need that sine of x completely alone, so I have to divide by -2. See how you end up at the same exact spot. Here's the problem. Sometimes you guys make up your own algebra rules. By putting that substitution, by putting those u's and y's and z's back in the problem, it kind of eliminates that. You can go back to your roots of algebra and deal with the problem in the roots of algebra. You're still going to get the same answers we see over there. But if you like the method I did with the u's, use that. If you see that a little clearer, use that. Either method you'll see gets us eventually back to the exact same location. So I don't care how you do the problem, you get to pick which method works good for you. Okay. Do we have any questions about example 2? Okay, let's keep going. Oh, we're not going to keep going. So for the 9-5A homework, tomorrow we'll do some more types of examples that uses some of our identities. So for problems 1, 2, 3, and 4, could you please just tack on the plus 2n pi when n is an element of our integers to every answer. For numbers 5, 6, 7, and 8, you don't have to do that. You could just, whatever answer you get, one loop around the unit circle is the answer you get to use. Do you see here how there's a bracket on the 0 and a parenthesis on the 2 pi? Isn't 0 and 2 pi the same location? So they say you don't have to write the 2 pi. We know it's covered when if 0 is an answer, you don't have to write the 2 pi as an answer. So for the rest of class, I want you to work on problems 1 through 8. We will do 9, 5B tomorrow. We'll practice a few more equations, but let's start with what you see here. Okay.